Next up, we have Leo Rozenberg, and he's going to talk about OCaml, which is a library he developed in OCaml at Mount Sinai's Hammer Lab. So take it away, Leo.
All right. Thank you. Is my mic on? I can't tell.
We can't tell you.
Oh, boy. You're telling me. All right. So first off, huge thank you to the Composa sponsors and the conference for putting this together and giving me the opportunity to speak. It's really excited to be here. Second thing is, this is a library that I'm going to present. It's a work in progress. I am not parking the domain name just ahead of time. I know it's really short and says the claim is OCaml, so you would think it's like the canonical math and statistics library in OCaml. If Jane Street wants to come along and release all of their top secret code and really release a machine learning library for OCaml, I'll gladly give up the name. It's just I find it really convenient to switch that directory. So for those of you who are following along at home, I think a lot of times people want to have the slides ready if they want to reference. The slides are here. I didn't realize that you're all going to have a really hard time getting Wi-Fi. If you're currently on your phone and when you want to download them, go ahead and grab the URL quickly. I'll give you a couple seconds. All right. Let's go ahead. So brief background about who I am. I'm a software machine learning developer at the Hammer Lab at the Icahn Institute for Genomics and Multiscale Biology, which is Mount Sinai's medical school. And we kind of work at the intersection of biology, computers, and math. A lot of our problems that we deal with are kind of ad hoc, but we should try and seek out different difficult computational problems. And we're really strong advocates of open source software. So part of the work that I was doing, I was like, okay, well, I want to make sure this open source is available to the community to get feedback. My actual background is in finance. I've worked for about 8+ years developing, high frequency trading stuff, stat arb, all that fun stuff that I'm sure is well represented in this building. So I'm fairly knowledgeable about that. And the last thing which I want you to know about me is I am very much a type addict. Like when I'm at a REPL to get the juices flowing, okay, how do I structure this computation? I'm going to start typing. I'm going to looking at the types. For all of you, the Haskell folks out there, having set plus T in my GHCI is pretty crucial to my existence in the Haskell ecosystem and understanding what's going on. And so now, just to shift briefly, is to be upfront about what am I selling? What's the purpose of this talk? Is I want to get you involved in OCaml. I want to get you involved in this project because I actually think that a typeful machine learning library is really important. So get involved. Let's have conversations at the conference at other times. File an issue. Try it out. See what's involved. The purpose of my talk is I'm going to give kind of a brief demo, show you a little bit of the layout of the library. Then I'm going to do a fairly involved demo. Then I'm going to share some observations about OCaml, some more observations about machine learning, and then if we have time for that, I'll talk about testing. I think that there are a lot of really interesting problems within the domain of machine learning and statistics for program language-minded folks, and I think we shouldn't let all of the people who are just in Python and whatnot have all the fun in implementing some of these things. I think if you're really interested in thinking about this stuff, that machine learning is just so ripe in terms of these interesting problems. So I want to motivate you. And lastly, I want to say that I think it's really important to get this stuff right. These are tools that we're using to do a lot of interesting analysis, and whether these tools are correct or whether they're precise isn't a really important question that I think is important for us as software engineers to address. One of my colleagues, Sebastian Mundet, who gave a talk here last year, really likes to point out that computers are really fragile, and even more so, developers, we make mistakes all the time, and having strong systems to curb those mistakes is really vital to having productive software. And so within this field, I think it's really important, especially you hear every day how data science is the next sexy job and whatnot. Analyzing data is getting more and more important to businesses. And I think that as software-minded folks, I think it's important for us to contribute in that conversation. So just to get get started and let's just dive right in. OCaml is really easy to install. If you have OPAM, which is the OCaml package manager, I don't know how many of you are familiar with the OCaml environment, but nowadays it's really simple. If you could just brew install OPAM, and then OPAM initialize, and then you can manage whatever libraries you need, and everything is really easy for you. So OCaml's available, OPAM install OCaml, and you're good to go. But then when you open up UTOP, once you require OCaml and load up, you're just going to get the 6 basic top-level categories that packed modules that I've put together. I'm just going to try and be a fairly quick rundown of them. The first one that's up there is util. I think of it as more of like a pervasives module that you should just open by default for same type of capabilities when you're required to deal with data. I have things in there where dealing with are you having a NAND, checking for that correctly. When you want to add up a whole large number of floats in an array consistently and accurately, I've written modules for that. So just a very convenient type module. The next one, which I'll address, is something I called uncategorized, and it's really just kind of like a work in progress. There's a whole bunch of packed capabilities which I've put into it, the different modules, and the work there is really kind of divided into 2 parts. It's kind of like special functions that you need to do, you need to use in statistics and machine learning, and then there's essentially the workings or the beginnings of a linear algebra type stuff. So, in functions, you'll find something like the regularized lower gamma, which I'm sure all of you know what that does. And then in solvers, there's something I've implemented, Newton's Raphson method. And I actually put this up here to demonstrate what I think is one of the most beautiful instances of a typed expression. And it actually takes me back to when I first started learning how to program, and when I learned about OCaml actually from Jason Hickey at Caltech over 10 years ago. If you remember the guy who wrote the original OCaml book, he says, okay, like this is how you define a function. And now I'm going to show you how you can create a higher order function of its derivative. And then we're going to use that to create actually a method to solve it. And then this very beautiful composition of functions and types to demonstrate and how to solve a problem. And so I've always kind of really liked this demonstration and utility. And the last thing that like I said, in uncategorized, there's like some stuff for linear algebra to get you going, and mostly like I just demonstrated, this is what the interface for SVD looks like. There's two more modules quickly. Online is something to do really stable mean and standard deviation calculations when you're folding over data, because one of the most common errors in calculating standard deviation is that you have a massive cancellation in error terms, and sometimes a more stable algorithm is one that folds over the data. Unsupervised is the start of basically unsupervised learning methods, and right now the only thing that I've put in there is principal components analysis. See, this is the interesting thing about CSS is if you hit plus, you go down, and then you go down, and so I'm at the top of it. Oh God, I have no idea how to do that. It's too late. It's not typed. I'm sorry. I don't know what to change.
Is there a little magnifying glass you could drag over?
Yeah, please come up. Like I said, the slides are available online, so I apologize. So statistics is another module which I put together when you want to get dirty with data. It has things like if you want to measure kurtosis and different distributions when you want to calculate the cumulative distribution function, the Poisson cumulative distribution function. I put in some hypothesis testing in there for you because this is honestly one of the motivations for writing this library is like I never remember how to do hypothesis testing. It's this thing I learned 10 years ago, and every time I have to look at a library, I understand the math behind it, but the correct order and invocation is really important for me to write down the types to remember that. And then there's last thing, a sampling module if you want to generate null distributions of random data that I've put together, which is actually fairly important in my line of work of bioinformatics. So just to finish off the tour, the main other modules that I've put together are some regression, where you want to fit linear models to essentially float type data. I've implemented various capabilities for if you want like univariate and multivariate ones. I've also been playing around with this Tikhonov regression, which is a much fancier form of ridge regression, where your prior, so to speak, is full blown on matrix as opposed to just one set of lambdas. I don't want to get into the weeds of the details there. Just I want you to know that it's there. And then the last module that's available for you is a classification, and that's when you want to learn associations between data which has a class and a feature, and given a feature, you want to figure out what the class is. And I'm going to use classification to actually give you a demo. The two main methods that I've implemented in classification right now are just naive Bayes and logistic regression, and within that scope, I've given you different various capabilities. So I'm going to dive right into a demo, but before I go there, immediate reaction might be like, oh my god, you haven't implemented LDA, you haven't done the following, and yeah, I'll totally admit that I'm like 0.01% of SciPy at the moment. I'm constrained by my time and ability to write this stuff, which is, I'm always eager to anticipate, to receive pull requests, and if you're interested in contributing, and also maybe somewhat sneakishly, I've not implemented some of this stuff because honestly, I'm not certain that like my implementation or my interface that I've exposed is the best one. So if you think that I should do things differently, please, I'd be welcome to look at different implementations and debate the merits of the representation. So I've kind of left some of the stuff out of the library. So let's do a demo. The source code for this demo is also available in the repo. It's under source scripts MNIST example. I was going to do it live, but when I went through the dry run of this talk yesterday, I realized that there's just no way between flipping back between the terminal and showing the demo that it was going to succeed. So my apologies for actually stepping through the code with you. In hindsight, I think that would be a lot more. It'll be much more formative and allow me to communicate how I'm thinking about the structure of this problem a little bit better. So the example that I want to do is I want to classify digits. In the machine learning world, this is a famous data set called MNIST. It was curated by several very, very famous neural network researchers. Jan LeCun, who's at Facebook, and I'm sure some of these people are somewhat in the news these days. I believe Cornelia Cortez is at Google, and I'm just going to guess that Christopher C. Burgess is probably at Microsoft, like the other three lab that does AI. I could be wrong about that, but I'm not certain. And so MNIST is a challenge where you're essentially given an image like one of these, and the task is classify. Like, tell me what digit this is. Seems pretty straightforward. You're given a square of grayscale values, and you're asked to determine it. This image that I've shown to you, just to give you a demo of how really good we've gotten on the field, is some of the best neural networks. In the test set, these are the only mistakes that they make. So these 35 examples are it. And so I believe that the top right number that's associated in this demo is the correct value, and the two bottom left are what the neural network thinks are the most likely values. So in a lot of cases, even though it gets it wrong, like in this one, the second most likely one is actually correct. So in terms of where we've gone in the field, it's pretty, it's very somewhat unbelievable. And MNIST is when you go to machine learning conferences, it's like a pretty standard benchmark. Like everybody's trying to either outdo MNIST, the previous benchmark of MNIST, or comparing their performance against it. So I figured it would be good for a demonstration. Yeah?
Is it the person who wrote the thing who decides what the correct thing is, or is there an official leader?
I don't know. Honestly, I really don't know. So just to I believe that NIST was compiled by, the original data set was compiled by NIST, which is the National Internet Standard Body, from, I believe, a census. And then Jan LeCun and the other, his collaborators, what they did was they took these images and centered them and pared them down to very, very bare bones so that their computers, like back in the 90s, and could handle this data. But I believe NIST actually did all the correct labeling of these digits, so that was just exported. Yeah, for some of these, obviously, like I would be just as like, is that a 9? Maybe. So, in terms of just showing off OCaml's capabilities, I want to just use a pretty standard techniques for this. Let's use a multi-class logistic regression. And as I'm sure that all of you know, to implement multi-class logistic regression, all you have to do is just minimize a cost function. I'm sorry, I forgot to insert it. But
This is the heart of the talk.
yeah, except I don't really want you to know that equation. Like, it's important and it's valuable to the machine learning community, but this is not that kind of conference. And I'm sure half the people might know the equation, some of them might not. And there's terms, regularization and whatnot. It's hairy, but that's not what I want to describe describe multi-class logistic regression as. I want to describe it to you as really it's a result of a functor. And it's how I want to choose to think of it in OCaml, for example. So you would, just to give you a brief description, once you've opened a classification, you're going to have a module which describes how you want to encode the data. Once you've given that encoding of the data to the functor is going to return to you a type which actually allows you to perform the classification. So this module at the very top, continuously encoded data, has a class and a feature. These are in this sense, the classes that we're trying to learn are 1, 2, 3, 4, 5, 9, and 0. I would have used class spelled out, but obviously that's a reserved keyword in OCaml. I thought about going German with Class, but you do the best you can. Pull requests welcome, like I said. We have a defined feature. In this case, our feature is just going to be an array of 78 times 78, 28 times 28, it's like, I think 784 field float values, which describe each of the values at each of the pixels. And then I have some, transformations like given for your encoding, how to transform it, and a value to determine the size of the encoding. And then what you get back is this multi-class logistic regression capable module. And what it does is, so just to go briefly through all of these types, the first 3 types, it just, again, imports the class and imports the feature. Then it has a type for what I call the optional arguments. And I'm just going to skip that for a second. I'll get back to it. Then it has the actual type, which is going to do the work. Afterwards, what I'm going to do is I'm going to give you the opportunity to evaluate this class regressor. In other words, this classifier, to actually do the classification. And the way this type should really just be given a feature, return to me a set of probabilities over those class. And that's what this is. And it says class probabilities at T, but it's really just a list where an association list between the class and the associated probability of that class. And then the other important method in this is how do you estimate this this classifier? How do you actually go from learning given your data to a classifier? And here I've specified that our data is just a paired list of class and features, and given such a set of samples, give me a classifier. So just to give you a little more of the details, I've moved all of the optional arguments into a unique type for the express purposes of afterwards, so you don't have to worry about them. But the other reason is that now it becomes really easy for you to say use different classifiers in a comparison, because the actual interface that's exposed by this classifier is uniform across all of them. So that gets very useful for meta type of work later on. And then this is a little more specific about the capabilities of this classifier if you want to list them ahead of time. Okay, so Continuing on the script. So when you load up the data, it actually, I wrote a little library called DSFO to make it pretty easy for you to load up that data in this particular example. You actually get a really giant array of 794 values times 60,000 columns for the training set. By the way, this layout has to be credited to Marcus Model, who's over there, for coming up with this really neat, I think, syntax for describing arrays. And so this is, and going back so elegantly. And so at the very beginning, you have all of your this is your feature, and then you have the label, which is just encoded at the bottom. If you want to actually see what these look like, and I'll openly admit that one of OCaml's major pain point is just visualizing data. OCaml is really terrible at it, but clever developers will be clever. And so one of the things I always was happy to do is be able to transform this data into a form which is easily viewable on the REPL. So this is a 2. As you can clearly see. If you want to play around with it and join it, get in the matrix of what is MNIST, there's a script on there. It's pretty it's a lot of fun. And I actually weirdly think of this as actually a better visualization than just some grayscale image. It was it's really hits you of what the medium of our computation looks like as opposed to an image. But okay, so moving on. So like I said, how are we going to encode the data from NIST? I think OCaml makes it pretty simple for you and straightforward. We know what our class is. We're classifying integers. I could have done unsigned int. I could have done labeled a variant of 1, 2, 3, 4. But I just for convenience, I just went with int. Our feature is, like I said, the float array. These are all the values of the individual points. Our encoding is, well, we were given a float array, and we want to transform into a float array, so our actual encoding doesn't do anything. It just returns the argument. And the size is just 28 by 28 for values. I have some plumbing here to convert it into nicely for the classifier to convert the huge array into association list. This is not that important, but it's there. And then actually we end up applying the functor. And I've already done I guess I've already went through the description of all of these values and types. And then when you actually want to go ahead and estimate a classifier, you just tell it to estimate. I've added some little bit of tidbit of tolerance, this little modification of the tolerance, and that is that underneath the hood, in order to do multi-class logistic regression, which I'm trying to give you a nice black box over, you have to twiddle sometimes with your mechanism, which converges to. There is an iterative algorithm which iteratively computes this thing called the Hessian, which I don't want to describe to you, but there's details, and there's one parameter which I want to expose to you, which is the tolerance of these details that I want to kind of make it exposed to you outside, but not give you everything. And so I will openly admit that in order to get this to converge, you have to play around a little bit with the tolerance. But it's not too much work, and in general, most of the time, that the default tolerance works pretty well. So this runs. It actually takes roughly about a minute of actual CPU time. I think the real reported time is on the order of 3 or 4. When I've played around with the default Python implementation, I think it's a little bit faster. But then again, I haven't dug into the details of making sure I have the absolute best installed version of BLAS or LAPOC underneath the hood, and I haven't really gotten into. I'll admit that a lot of the time is spent at actually just moving around the data from one representation to another. So I haven't gone down into, like I said, the details of optimizing it. So because for me, the performance of this takes a minute in Python and it takes a minute in OCaml, I'm pretty fine with that. So then we can evaluate it, and evaluating it should also be really simple. That is, I have my test set, and basically what I'm saying is just okay, here's the class which I already know the answer, and then evaluate based upon the feature and give me whatever is the most likely class, because I'm going to get a probability for all of them. I can always just pick whichever is the most likely, and that's my test data. How many did I get right out of 10,000? I got 9,263, which I did pretty well, 92% correct, and which is I think pretty decent for not a lot of work and pretty easy description of the interface between and a pretty good description between the problem domain and getting a result. Now here taking off my software engineering hat and putting on machine learning hat, this is like on NIST a 92% correct result is like, dude, why did you even bother, right? It's like when you go to a machine learning conference, it's like it's 97% or bust, right? It's really like you have to have a novel result at this point. But I think from a baby steps, so to speak, from a the design perspective, I think having a really clean interface is more of the appeal of this project right now. And as a starting point for this method, 92% actually is, I think, pretty good.
So on the things that artists would, do you have the 8% that artists would, do you have confidences around those or threshold confidences that you can fiddle with to kind of see, okay, those, I'm not as confident in those, so of course they might not choose the right thing.
So that's a really good question, and so it kind of gets to part of the motivation of my talk, and that is that when I gave you this kind of interface, I purposely so I didn't mention these other things like the coefficients or the class order, which are the things you can derive out of multi-class regression. Multi-class regression, the way it works is I have probabilities for all of them, which is what I'm trying to represent with this type. So you can always choose the second most likely candidate, but I'm not actually given confidence upon my probabilities. You can derive those, I think. Not a stats expert. I think you can derive those, but again, like I haven't exposed those. But my point, moreover, is that there are some classification methods where you can't do that. You're not given those probabilities. And what I think is really important for this library to do is to correctly represent what is possible with a method and what is not possible with a method, so that a novice who tries to approach this problem from the beginning can see that in the result of their function. Now, it really might be the case of you have to file an issue like, how come you haven't implemented this feature? I want it now. And it really, I think a full feature library would actually address it, saying this is not, you're not logically thinking about the problem correctly. It just doesn't, the peg doesn't fit correctly. So that's a brief survey of OCaml's capabilities. I was going to do other demos about how to trade stocks and whatnot, but I don't know. I figured one would be enough, and we can just move on. And if you're interested, I'm sure you could all just play around. So I wanted to share some lessons about about OCaml and whatnot. The first, these aren't really deep lessons, so I think a lot of OCaml developers, but I think maybe this might address some people who don't spend a lot of time writing it. The first one is that using local opens and overloads really gives you a really easy and cheap DSL. So a local open is you can just give any module. You can open it you can say let open in a given line, or you could just say module name dot, and then within parentheses that module is considered open. And I think it's a really powerful way to really write really concise and cheap DSLs when you want to represent some logic really concisely. One of the pain points that I frequently hear amongst somewhat novices against OCaml is that if you got to multiply two floats, you got to do a star dot, or if you want to add, you have this dot thing and everybody forgets it. And after 10 years, I still forget it. It happens, but I don't find that it is a very valid criticism of the language, because it's if you want to be type safe, you want to be type safe the whole way through. But if you want to have an efficient representation of your logic, well, you can just do that with a DSL. And I think local opens are actually a really great way of doing that if you want to write your logic concisely. I use this trick in some of the special functions calculations where it's you take the product of this, and it's the square root of some other things, and it's just nested, and it gets hairy. And you really wish, oh man, I wish I could just insert some LaTeX in here, and it's like this is my function of what it looks like. But this is, I think, a second best solution. I think it's pretty well. And you can do, I think you can extend this technique to much more complicated things if you have linear algebra type structures. The next lesson that I've learned is that I think it's separating the optional arguments into a separate type can be really useful, in particular if the module that you want to export afterwards, you might be using in an interface with other modules. So you just define a type which you call your optional args. You give it a default constructor. You give it a default value, which could really just be calling that optional argument constructor with unit. And then the thing which does the work can take it or not take it. I think this is a fairly nice way of separating concerns. And the last lesson, it's not really a lesson so much as I don't necessarily recommend this, but it's more of what I call a cheating heuristic if you want to write fast OCaml. I just say just write C, and then just take the different language idioms and convert it to OCaml, and that generally gives you pretty fast OCaml. It's not. I don't recommend it, especially if you want to have a type safe and a pure approach to it. But if you're really in a section area where it's critical and you're like, okay, how do I write this code so that it's pretty fast? Just do this something like that, and you'll be fine. This is just 2 implementations of how to do Gahan summation, which I'll get to later. So now I'd like to just shift briefly and really talk about give you 3 reasons to use types in machine learning. And the 3 reasons I'm going to give are kind of broken down along a continuum of modeling the problem domain, then at the interface of that between that domain, and then getting into the world where essentially all you're doing is manipulating floats. Because machine learning is all about learning functions that represent those things in the real world. And the question is how do we do that? And well, so far all of our computations are just done with floats. Unums haven't hit yet. And so converting that pathway, I think, is really important. So this point, I think, is pretty obvious to, I think, a functionally minded audience, and that is that types in your problem domain are absolutely key in terms of allowing you to embed the knowledge that you have about the problem domain into your program or whatnot. So this, I think, is a no-brainer. When I work in bioinformatics, we have these things called amino acids, and I have sequences, I have characters to describe them, and so forth, things like that. The second reason is being specific at the interface. I think with typed languages, we can be very, very precise about what we mean. So when you use things like an R or Python, which are R or SciPy, they have really powerful capabilities. And I'll admit that OCaml is this versus all the other stuff is tremendous. But a lot of those libraries have knowledge which is embedded in them because a statistician wrote that knowledge, right? A novice comes along and doesn't get that knowledge right away from the library. And the common refrain is RTFM and good luck. But that honestly just to me doesn't cut it. Do you want to think about your system as the way to gain knowledge about it is Stack Overflow, how do I do this? Or do you want that knowledge to be represented for you in the types that are embedded? All right, I have 5 minutes. So we'll go really quickly. And the last, so to finish this point is I think we can be much more accurate about doing that. The last point is more about when you think about the work that is being done by these algorithms. When you think about regression, classifications, or other methods, I don't think that they're objects. And here I'm using objects in a very, very vague thing. But what I'm certain of is that they're not some loose association of dictionary of methods of fields and whatnot. I think that they're functors. I could be wrong, but I do think that there's some kind of typeful transformations of our knowledge to capabilities. as a very first step of what I think OCaml is trying to do is I'm trying to expose, this interface between like, okay, what does it mean to do linear regression? And it's like, oh, well, you have your float array of predictors, and you have your float array of response, and then you want to give a result which is your coefficient, which is just a float. And okay, I'm even ashamed to write this because really I should have labeled this like your predictor and your response are different, right? Like I'm sure that there's been times when you've like put in regression and you swap the two arguments and it worked, and you're like, okay, I have a beta, okay, I'm done. You go to your boss and he's like, no, you have the wrong value, right? Like, and in a lot of cases this is really important. And so a classifier should give you pairings of data to send the ability to go from a feature to a set of probabilities. And like I said, this is really like step 0.01. I haven't implemented all the methods that you may need. This is just the very first beginning of trying to expose the precision boundary between the world and how we want to get at these methods. And then the next step is like, how can we do this thing even better? Like, right? So when you perform linear regression, you make these assumptions such as that like your errors are normally distributed, and like I as a machine learning guy know that, but me as like an intro software developer guy, like I may not know that, right? Like you have this library which you use in garbage in and garbage out, and so I think getting to the next step of having really strong interfaces which describe the logic and the transformation the machine learning is engaged in is going to require stronger types. I'm not too knowledgeable about whether dependent types are the answer, whether different proof theorem systems are the way forward. I'm just saying that this is the next step of where we want to go. So I have about 30 seconds. The last reason. This isn't like a really good reason, kind of a 4A, and that is I really think that machine learning can solve a lot of the meta problems that you get in. I'm sorry. I think that types can really solve a lot of the meta problems you get in machine learning of like segregating your data into training and validation, and all of that gets done and refined for you at compile time, which is fantastic. So you don't end up making these mistakes. So I wanted to save some time for questions, and my timer for 27 minutes is done. So I'm not going to talk about testing, but we can talk about that afterwards. Let me just quickly jump to. I want to say a thank you to Jeff Hammerbacher, who's my boss in the Hammer Lab, Sebastian and Isaac, who have contributed with reviews on it. Carmelo, who I don't think is Carmelo, who really helped start a lot of the development on OCaml early on. And honestly, I'm going to admit that I'm also really standing on the shoulders of giants who've done work before me. Marcus, who's developed a lot of like machine learning libraries, which are like if I'm doing address in the beginning, Marcus just said, "Man, this is boring. Like here's GPR." And Christoph Tressler, who's like given us some really good bindings to other libraries. So I wanted to just thank you give a thanks to those people before I conclude.
All right, we have time for one question.
Anybody but this guy. I know him.
Although I'm a full-time OCaml programmer, I'm not actually clear on OCaml's use for numerical computing. I've often heard that the compiler doesn't support numerical computing that well, and it's not you wouldn't want to write numerical algorithms in raw OCaml. Are you bypassing that issue entirely by having bindings to C and Fortran libraries, or is that a concern? And if it is, what are you doing about it?
Okay, so first address. I don't necessarily agree with that. I don't think OCaml is good for it. Like that C example really kind of illustrates it. Like when Xavier Leroy and the other developers were writing it, they were really very, very performance minded. I think about describing getting really good performance in OCaml. So there's some stuff like if you want to evaluate special functions, the small allocations that compiler is going to use. I don't really think there's a really good reason to use bindings to a special library. Honestly, I'll admit I did use bindings to a special library because the probability of me making an error is very, very high. And this is constraint optimization in a program. So I wanted to use something which works. It's definitely an area which, like, if I had, a vacuum of time right now where I had hours to work on it, I would definitely be really working on replacing it, because I think that OCaml can do it a bit better. With regard to other things like multiplying arrays and things like that, yeah, at that point, when you have to manage lots of big memory and you specifically want to make sure that it's optimized based upon loading it all in memory at once and all these special instructions, there I definitely do think that there's a place for wrapping up libraries. So it's on the one hand, I don't think it's as bad as people make it out to be, and on the other hand, I think that you in some special instances there are definitely cases where you would want to use it. I don't know, did I answer your question fully? Whew.
All right, guys, let's give it up for Leo.